The long-term work plan for CSI was developed through a series of workshops with academia, industry leaders, and utilities, including East Bay Municipal Utility District, Los Angeles Department of Water and Power, Metropolitan Water District of Southern California, and San Francisco Public Utilities Commission. Some of the innovative and groundbreaking, and I mean figuratively and literally, research undertaken by CSI include state-of-the-art lab and field testing. For example, testing earthquake-resistant pipe from around the world using fault simulators, smart sensors and robotics, big data and machine learning, and multi-scale computers modeling and simulation. Our featured guests today are Professor Kenichi Soga and David Katsev. Kenichi Soga is the Donald McLaughlin Chair and a Chancellor's Professor at UC Berkeley. He is the Director of the Center for Smart Infrastructure and is a faculty scientist at Lawrence Berkeley National Laboratory. He is a special advisor to the College of Engineering, Dean for Resilient and Sustainable System. He obtained his bachelor's and master's of engineering degrees from Kyoto University in Japan and his doctorate degree from University of California, Berkeley. He was professor of civil engineering at University of Cambridge before joining UC Berkeley in 2016. His current research activities are in infrastructure sensing, performance-based design and maintenance of infrastructure, and energy, geotechnics, and geomechanics. He is a fellow of the UK Royal Academy of Engineering, the Institution of Civil Engineers, American Society of Civil Engineers, and Engineering Academy of Japan. He is the chair of ASCE Infrastructure Resilience Division's Emerging Technologies Committee. He received a UC Berkeley Bakar Prize for his work on commercialization of smart infrastructure technologies. David Katsev is a senior civil engineer at East Bay Municipal Water District. David is the engineering lead for East Bay Mud's Pipeline Rebuild Initiative, focused on creating an innovative culture, increasing the pipeline replacement rate of East Bay Mud distribution mains, and implementing change within a large organization. David has over 20 years of experience in engineering, a master's in ocean engineering from Oregon State University, and bachelor's in civil engineering from Tufts University. Okay, so as far as today's presentation goes, our 60-minute webinar will include approximately 40 minutes of presentation by Kenichi and David. We'll then transition to an interactive Q&A session, like Melissa mentioned, for the remainder of our time. It is now my pleasure to introduce Kenichi and David to the group. David?
Thank you so much. I'm going to share my screen.
Hello, everybody.
Hi, everyone. Do you see my screen?
Yes.
Yeah, we can see
Yeah,
it.
great. Thank you. Yeah, thanks a lot, Trish. So I'm Kenichi Soga. I'm professor of civil engineering here at UC Berkeley, and then we'll do a presentation with David Katsev from East Bay Mud, and we'll do turns together and then interactive between two of us. And I just want to start with this particular center started about 2 years ago with sort of a phase 1 support from East Bay Mud. And now we're expanding the collaboration to phase 2 with LADWP, MWD, SFPUC that you know very well. And also, we also work closely with the other infrastructure owners like U.S. Army Corps of Engineers, PG&E, Caltrans, and State of California Energy Commission, California Energy Commission. And the spirit is not just only sort of a water industry, but really learning each other from infrastructure industry. How can we change the way we do infrastructure management? And this is what the spirit is about. And how do we bring emerging technologies into the market? So I'll pass it to David.
Yeah, and I'll just kind of add there, while we've kind of focused on the California utilities, MWD, LAWP, and SFPUC, we're open to working with other utilities around the country. So it's just, we figured we'd just start with California and then we'd branch out from there. So, as Vladimir says, I'm the lead for the rebuild program here at East Bay Mud, which has been going for about 10 years now. 100% focused on our distribution pipe, our 4,000 miles, ramping up our replacement rate, but not just doing it the way we've always done it. Challenge, you know, our kind of mission is really to challenge the status quo. Look at everything that we do from start to finish, from planning, design, construction, maintenance. How can we do our work better is the constant question that we ask ourselves each and every day. And that's the innovative culture. And I think the rebuild culture, what we've done in the last 10 years, we've doubled our replacement rate. We brought in a lot of innovative materials. We're looking at different ways of doing things in construction. Just that whole mindset, all that work has really led us to where we are today with UC Berkeley. And just the collaboration that we have. The poster that you see there is really our you know, that's just kind of what we go by day to day in terms of our work. The workflow there in terms of challenging the status quo, and then everything around the workflow is really different things that we're looking at to improve our work. So next slide. You know, we live in an area where there's a lot of risk in our area here. Of course, on the right there, you know, you can see Oakland, the San Francisco Bay right there. The dark line right there that Kenichi kind of can go up and down there, that's the Hayward Fault. And so we know that that's going to go at some point. We want to install a resilient system, a hazard resilient system. We have a variety of different pipe materials that's shown on the left side. All the different colors there represent different types of materials. So one of the things that the rebuild program does in terms of research and innovation is really to look at materials. What are the best materials that are going to be able to withstand ground movement from an earthquake? But also we have other risks. You know, we have landslides in the area, liquefaction zones, other kind of hazard risks that we have to evaluate. So that's always at the constant top of our list in terms of what we need to put in the ground. We want it to last. Of course, we want it to last a long time, but we want to make sure it's going to be resilient. So, which has led us to universities. We used to go back to Cornell University to see the large-scale fault rupture test back there. That's the picture in the upper right-hand corner. The blue line is the where a pipe is buried below the sand there, and the yellow angle right there is the fault rupture. So we used to go back to Cornell to see these fault rupture tests of different materials that you can see there. You know, the ERDIP, the IPVC, the PVCO, the aqua pipe. These are examples of materials that we've seen tested at Cornell. But a few years ago, an opportunity came up where the professor at Cornell retired. The professor, Tom O'Rourke, has a very good relationship with Kenichi Soga. We decided to move the whole testing apparatus over to UC Berkeley. And that's part of what started the whole Center for Smart Infrastructure. So now, instead of flying across the country to Cornell to see the tests, and by the way, CU Boulder has some testing too, I can just walk out the door here, get in the car, and drive about 15 minutes up to the CSI, the Center for Smart Infrastructure, and I can see the test right then and there, along with my other colleagues here at East Bay Mud. So it's really convenient for us, but it makes sense. It makes sense because we're right here on the Hayward Fault, and we have these testing apparatuses right here in our service area. So that's a little bit of background to where how we've kind of gotten to here. And with that, I'll pass it back to Kenichi to talk a little bit more about what is the CSI. And like Kenichi said, we'll kind of go back and forth.
Yeah. So thanks, David. So the collaboration is really use a holistic approach to develop resilient systems through state-of-the-art lab, which you sort of saw, and then we'll give you more examples. Smart sensor and robotics. How do we bring these new technology into the market? looking at a lot of data. There'll be a lot of data coming from sensors, but we'll also already have lots of data. So how we can do that. At the same time, how does the pipeline level instrumentation affect the whole system level thinking of looking after our infrastructure? And obviously the challenge is the aging infrastructure, climate change, water supply, natural resource, emergency, and community preparedness. So even we start with pipeline testing, we're growing our activities together to look at these challenges. And the spirit is to provide innovative solutions to realize adaptive systems with the intelligence of life. Why it's adaptive? Because we tend to design our infrastructure for 100 years. David would like to prolong the life of the infrastructure to 150 years or 200 years because some of the systems are working well, but then he wants to know when to replace and when not to replace. Obviously, we know that the reason why we say aging infrastructure is because demand changes every 20 to 30 years. It's not just pipeline is degrading, the way we use is changing, and that creates issue to aging infrastructure. So rather than fixed design, can we make our infrastructure more adaptive to changes? And if you want to do adaptive change, you have to understand the real performance, the actual performance, and that's where sensors come in. But then the question is that what kind of sensors are good to monitor use for many, many years, for tens of 20 years to come? We want to make our aging infrastructure not to be aging infrastructure. It'll be great to say to our next generation, there'll be no more aging infrastructure. This is something that David likes to talk. Do you want to talk about this?
Yeah, I just think in the life cycle of anything, from planning, design, construction, maintenance, this kind of color-coded circles on the right there and where they are in the life cycle highlights where we can do research. We can do research in the modeling. We can do research in the design. We can do research in the operations and maintenance and construction. So there's a variety of areas where East Bay Mud has challenges, and we can link up with UC Berkeley to do research and to come up with solutions that we can then implement. So this kind of shows just the overall workflow and where we can all fit in with all the different challenges that we have.
Yeah. And can we think infrastructure as part of the circular economy? So how we reuse the material and that sort of thing is something that we all thinking about right now. UC Berkeley not only have the Berkeley Center for Smart Infrastructure, we have other centers that links to infrastructure, like Pacific Earthquake Engineering Research Center, information technology to be used for interest of a society, Berkeley Water Center. So some of you may know my colleague David Sedlak, who runs this. ITS at Berkeley, which is the Institute of Transportation Studies. So we're talking about pavement repavement after the trenching is done. The SIM Center is National Science Foundation Center, looking at big scale simulation, which I'll show you later on. And then Berkeley GMS Global Metropolitan Study is our colleagues from social science looking at infrastructure. So we're working together to create some resilient infrastructure for sustainability and equity. And RISE is one of the 3 initiatives within the College of Engineering to make the engineering for the society. In order to do that, we just don't do research. We want to make a sort of an innovation and create a market. So working together with you and infrastructure owners, as well as consultants, contractors, information technology, it's really finding innovation and it's showcasing it works. But then we need to create a market, smart infrastructure market, community-based resilient market. And how do we invest ourselves? The data that you have is a currency that we can use, and how do you bring that particular data set as part of you using that and bring it back to your own company and invest your infrastructure? This is one of the examples using some sensors. So this is a pipeline rebuild David has been talking about, which is crossing a Hayward fault. So when they were doing the rebuild, we actually put a fiber optic sensor. This is a distributed fiber optic sensor, which is a standard optical fiber used for communication. But when you shoot a light, every point a light comes back, and we understand a particular light coming from one particular location and analyze that, we can say, what is the temperature here? What is a strain here? And what is a vibration here? And by doing that, for every light coming at different location, we get what we call distributed temperature or distributed strain or distributed acoustic or vibration sensing. So if you put this in a pipeline, if a certain place strains, we can see what magnitude of strain that is and where is that happening. If you're having a leakage and then you can hear the sound, it can tell you what is the sound is and where is it coming back from. So for example, this is the pipeline where we put the fiber optics. You can see a line of fiber optics attached at 3 different locations. And I'll show you a video where we attach the fiber optics at 3 different locations. And we can, if the pipe bends by the fault movement, we will see a difference in strain at different locations, which allows us to understand how much this particular pipe is bending. So once you bury a pipe, you're not going to see for 100 years. So the spirit is that, can we put the intelligence on this pipeline so that we can monitor for the next 100 years, and therefore our next generation will be thankful for us doing this. So this is a sort of a trial to show the value of sensing, so that infrastructure owners like David will say, oh, this is useful. And then he can start to ask the pipeline companies to embed the fiber in their products. But in order to do that, so that's what we do. And once we bury our pipeline, we're not going to see it for the next 100 years. Why not embed intelligence during construction for future generations? Obviously, in order to create confidence, we have to show the value of sensing. So these are these facilities that we built in collaboration with East Bay Mud at UC Berkeley to try different testing of pipeline, at the same time putting fiber optics that we will trying to use in the field and showcase the value of sensing, of monitoring the joints, for example. So you can see cables attached around fiber optics, which will measure strain or temperature all along the fiber. And by doing that, we can get a continuous profile of strain around the pipe, for example, around the bell. And that's what we see. And you see a sinusoidal wave. And the reason why is that as you pull, this particular bell is squatting. And if it squats, you see 2 sides in tension and the other 90 degrees in compression. And that's why you see tension, compression, showing the mechanism of how this particular pipe is moving and reaching to failure. So we're doing a lot of testing on that. And this is one of the tests that we recently did with Kubota pipe, which is the 26-inch pipe. And it's a bending of the joint. And you can see the size of it. And the pipe is, it will elastically move up to 7 degrees. So the company says up to 7, we're confident that it will work okay. So we wanted to see how far it can go. So the pipe is pressurized. So it's filled with water with a pressure. And then as we do a bending to make this particular bend as much as possible until the pipe fails. So we're going 7 degrees, it's past 7 degrees, it's going to 10 degrees, and it keeps on going. There's no leakage, even though it's beyond the threshold that the company says it can go. And it keeps on going until 20 degrees. And then when it goes to 22 degrees, we start to see a crack, and then suddenly the water starts to come out. So a little bit later, you're going to see something happening soon. So now it's reaching to 22. And then it failed, and you can see the water flooding. David, do you want to say something on this one?
I just think that this is earthquake resistant ductile iron pipe, and that's one joint. And when we install pipe, we do many joints together. So, and this joint can move back and forth inside the joint. So, you know, the bending test is one test that we can prove, verify that the pipe is resilient, but we also do tension tests and compression tests and other tests just to classify the pipe in all the different tests. And we're going to install the Kubota ERDIP on a project coming up really soon. So this test is quite helpful for us.
David, do you want to talk about this pipe? Plastic pipe?
And we also look at plastic pipe. So we look at a variety of materials. And so this is a plastic pipe, and it has an external harness or restraint, we call it, which is the red piece you see there. And this is just another example of us bending the pipe to see how far we can take it until failure. We try to fail the pipe. We try to take it as far as we can with each and every one of the tests, just to see, how strong these materials are. We repeat the test several times, so we have some repeatability. And then we look at the FE analysis, the numerical model, to see where the stresses happen. This is another one. Kenichi, you want to do this one? Or?
Oh, you can go. Yeah.
This is also earthquake resistant ductile iron pipe. I think there's a video here that can start. Yes. This is an interesting test. We're with one of the other things that we're trying with the Center for Smart Infrastructure. Manufacturers do tests, other people do tests, but we're trying to be unique. And this is a very unique test that we did, where we've actually bent the pipe down. I think we bent it about 7 or 8 degrees.
Yes.
And then we pulled it in tension. So we had 2 different loadings, a bending and tension, to see how it responds and to see when it fails. We call this the biaxial test.
So this being bent for 8 degrees, and now we're pulling the pipe in tension. So I'll show you with a video with the background noise that you'll hear something. So we're pulling the pipe, and at some point, the joint breaks, but then you see a little bit of water, but almost no water coming out. And we keep on pulling the pipe as we see, and you can see the joint over here. But then you start to see a little bit of water coming out, but it's still keeping the water pressure. And we keep on pulling until it starts to have a large leak. So these are the tests that we do, and then trying to understand the actual performance of these pipe, and also measuring what kind of a data, strain, and details of the strain, because we do finite element analysis to understand the failure mechanism and what will be the weakest point, but would it break at the same place? Because if it's same place, we know that it's robust, that it will break at that particular point. We don't want to see a random break. So these are the tension tests, and then we do simulation, but the fiber optic sensors allow us to calibrate the data so that we understand the real performance of the joints. So this is for the tension test. Here's another one for the 4-point bending, where we start to bend our finite element analysis. And again, we do simulation to see which part of the pipe, as it bends, start to stress a lot. You can see the color of the stress showing where the stress concentration is, and then as you pull, what's going to happen to these pipes. And that allows us to understand the failure mechanism or sealing mechanism, and see how these pipes are performing and how we can improve if necessary. So you can see all these finite element simulations. At the same time, we want to move it to the field, because every pipe is different, every ground condition is different. So we want to make sure that we can monitor our pipeline in the field, and that's where monitoring technology and robotics technologies will be useful. So using, for example, satellite or LiDAR to look at landslides, or using some robotic technologies. This is the Boston Dynamics dog robot. Where can we use these robots to scan the trench while you're replacing your pipeline? Fiber optics you can embed on the asphalt pavement, so where you can put the fiber optics like this, and you repave it. Actually, if you have a dog running, you can see the dog running. Or if you run, you can see how people are using that particular road. So this is a bit like a touch screen of this particular road, and you can see how the cars are moving on the street. And then we can see the color, which is the magnitude of the strain as the car is moving, trying to understand who is moving, what kind of a safety we can provide to the pedestrian, for example, using this kind of technologies. And you can see that we can use this kind of sensing technologies for different cases like tunnels. This is a project with the Singapore government where they're putting this fiber optic sensing for 51-kilometer long sewage tunnel. And the point is to use this sensor for the next 100 years, because in Singapore, they're going to do a lot of nearby underground construction. And for the sewage owner, it's very important to protect their sewer when the new construction done nearby. We also have a project with a floating wind turbine, which is what's going to happen in California, where you have these moor lines, and the moor lines will have that fiber optics, which we can hear the noise. And the idea is that can we have this when the whales or dolphins sings, can we detect their singing so that we understand the environment around the floating wind turbine. Here's another one using the ground penetration radar. David, do you want to talk about this one?
Yeah, part of the construction work that we have, we are always digging in the street, and we don't know exactly what's in the street. So there's technology out there right now, ground penetrating radar, where we can survey what's underground, and then we can turn that survey data into a 3D visualization. This can help us in the design process to know exactly where we want to put our new pipe. Or B, it can also help us during construction. When our heavy equipment operators are out there digging trench in the ground, if they can visualize this, with their iPad, walk up and down the street, see things in 3D, then they'll know what's coming up. Hopefully, you want to do things safely, but maybe this can increase our productivity as well. So this is a technology that we're testing both in design and construction. The blue is the water pipe, the green is the sewer, and then the yellow is the gas. And so this is just kind of one example where we've applied this technology.
So once we understand the performance or monitor our infrastructure at pipeline level or road level, what we can do is to simulate each road, but then to the regional scale, like the whole entire Bay Area in one model. So for example, this is a road networks, and then there are about 7 million people live in the Bay Area, and every day there's about 50 million trips. So we model each individual 50 million trips going around in the Bay Area across a day, within a day. And then let's say if the Bay Bridge stops by an earthquake, what's going to happen to the traffic? Similarly, like when you have a water network, this is the East Bay Mud Network. But then let's say if you have an earthquake and if you have any pipeline damage, what's going to happen to the water supply? So for example, this is one of the examples that we do within the Sim Center, is that we simulate earthquake scenario. In this case, it's a Hayward Fault, 7.4 magnitude earthquake. And then when that happens, we know the ground shaking at different locations. We predict which locally how much is going to shake within that earthquake, and then assess each pipeline. What is the probability of failure of each pipeline? And then after that, we say, okay, these pipelines have broken. What is the water network? We do the hydraulic model to understand which customers will get water or how much they will not get water. But at the same time, so you can see sort of a average water shortage, but then we don't know where the earthquake epicenter is going to be. So we do Monte Carlo simulation to see what is the average, but then what are the standard deviation? What are the uncertainty? And at the same time, my colleagues at Sim Center do simulations of each red tag buildings. Each building, is it going to be red tag or not? Looking at each house condition. And by doing that, you can look at the interdependency. When you look at the recovery, if there's a lot of red tag buildings, perhaps there's no need to recover these water supply because people won't be living at that particular location. So with East Bay Mud and the others, we're trying to discuss how these sort of a different simulation can look at as an interdependency, and how do we look at recovery plan of our infrastructure to functional level when when a major earthquake happens. At the same time, what are things that we can do right now so that functional recovery will become faster if a big earthquake happens? So we've been working in the past year or so. We have done 4 workshops working together with the California Water Agency, including East Bay Mud, LADWP, MWD, and SFPUC, with the other organization, really to look at how we can work together in the area of aging infrastructure, water supply, natural resources, climate change, and emergency community preparedness. And then this is a next workshop, but we just finished this workshop recently. And then we're trying to look at, probably the next one will be looking at water supply and natural resources, how these sort of a big simulation can help us understand to look after the climate change and natural resources. And then we also have individual projects. We're working with East Bay Mud in the next 1 or 2 years, and we're looking for you to join these projects and work together. And that's why East Bay Mud is sponsoring the course, but hoping that you can join together on these projects. David, do you want to talk about some of these?
I just think, so these are some of the challenges that East Bay Mud's identified for research opportunities. And so what we do is we link our own subject matter experts in the different divisions, departments at East Bay Mud up with Kenichi Soga, and then he will find other professors at UC Berkeley or other programs at UC Berkeley to then create the team to do the research, whether it be on dams, wildfires, landslide modeling, pipelines, the items that you see listed there. So then we create these research teams, and then we also bring in other utilities, SFPUC, LADWP, and MWD right now, but there could be others, that outside of California that can get involved. I think the more utility owners we get, the better in terms of creating this team and this research. So this is where we started, but we know there's other areas to explore as well.
So we just finished our phase 1. East Bay Mud provided 1.5 million investment to do this phase 1 to really build up of that large scale pipeline testing facility. As you see, Cornell has been doing some testing, but then we want to go to bigger, larger diameter pipes because we see these pipes used in real. And then we've been doing workshops and then working together with East Bay Mud to really build up the basic so that we can go to phase 2. So we're starting to looking at the opportunities for phase 2. SFPUC and LAD have committed some of the funding that for further to create phase 2. We're talking with MWV, but we like to start building up the sort of community to go to the phase 2, expanding the pipeline testing facility. Like you want to look at like 104-inch diameter pipeline bending, which MWD uses. And we want to look into opportunity to expand our testing facility, but at the same time looking at more sort of developing a midterm and long-term business plan, working together with you. And how do you make Berkeley as a hub with the other centers that you have seen? And obviously, we cannot just keep on getting funding. We have to deliver. And then phase 3 will be self-supporting innovation center with data analytics and that sort of thing. And we start to develop business models together with the water agencies. So by wrapping up, what we want to discuss today was to showcase our initiative in terms of doing large-scale testing facility and leading to smarter construction and maintenance savings to make in this rehabilitation of our aging infrastructure and energy management using monitoring and robotics technologies that we see in practice and big data and the AI cyber threats. And the obviously goal is about sustainability and community resilience. However, we really need to bring next generation to be excited about infrastructure engineering and the field that we're working on. So you can see that we have developed East Bay Mud sponsor course. And maybe David, do you want to talk about that?
Yeah, we developed a class. We taught a undergraduate class last fall Civil Engineering 112, focused on water and wastewater operations and design. We had 25 students. We had different East Bay Mud experts go in to teach the class. We had laboratories where we went out and we saw facilities. And then we had students do research projects. It was the first time we did it. We're going to do it again. You know, what Kenichi said, getting students excited about, you know, the water industry and research. I just had a student reach out to me. She's in her 4th year at UC Berkeley. She's going to be taking a data class next year, and she reached out to me because she wants to do a semester-long project with East Bay Mud on some data on looking at pressure in our water distribution system and forecasting main breaks. So you know, we got the students excited. She wants to do the research, and now I'm going to link her up with some of my engineers in my group to work on the project next year. So just a nice example of how we've I think we've started to inspire some of the students at Berkeley to want to come into the water industry to work.
Yeah. And that's the major, I think, contribution we can make at UC Berkeley and other university, which you know, to really inspire our undergraduate and graduate students to go to our industry. So to showcase that we're innovative, we're developing and want to do emerging technologies into our market. So this is my final slide, saying that if you cannot measure it, you can't improve it. That's what Lord Kelvin said in 1883. And that's what the spirit is, that we do see emergent technologies that you can measure now in a way that we can improve it. So this particular CSI is not only a think tank, it's really more importantly, it is a do tank. Let's do it and then measure it and then improve our infrastructure. Thank you very much for listening.
Thank you, Kenichi, and thank you, David, for this very fascinating presentation. We are now ready to begin our interactive Q&A session. Melissa previously went over the rules for the Q&A session. Melissa, will you please do us the honors and kick it off?
Yes, thank you, Vlad. So I will read off the questions that have been provided in the chat. If you have any additional questions, feel free to add them. So our first question, how do you prioritize the areas, subjects for your research?
In terms of pipelines or what natural resources, and that, maybe David, you want to talk about that?
Yeah,
first?
I think what we did is we had those initial workshops to see what were those big challenges from water utilities, that, you know, these are challenges that you can't solve on your own, where you need UC Berkeley, you need the research. So how do we prioritize those first set? We got together with everybody and we did these 4 workshops, and we itemized, you know, where are those priority areas we want to do the research. So that's what we did, and I think we're going to continue to do that. Because, you know, so that was our process for that.
Yeah. So the workshop we had was on the aging infrastructure and pipeline rebuild and that sort of thing is the first one big specific workshop. The second one was emergency preparedness, but then recovery. How do we think about what can we do right now to improve the recovery? And then now we're discussing, probably the next one will be on the city scale modeling and all these things that we've been working on, and then also natural resources area.
Thank you. Our next question, how accurate is the subsurface digital technology that you've been testing?
So there are several technologies that we're looking at, and maybe David, you want to talk about the GPR, ground penetration radar part?
Yeah, I think the GPR technology, it really depends on the quality of the soil that in the environment that you're testing. We've noticed in some areas the signals are very good, but we've also noticed in some areas where our soils are really clayey, signals aren't as great as in other areas. So we don't think it's a solution that we can use everywhere. But we do, I think our next round of research I have about 30 different projects for upcoming in the next couple of years. We're actually going to drive the GPR technology over those 30 different project areas, and we're going to find those areas where the soil conditions are good enough to give us really good signals.
Yeah. So
Thank you,
in terms
David.
of, yeah, and then for fiber optics technology, you saw dog running, which is a dynamic strain that that goes to nanostrain level, which we never seen before in terms of the sort of accuracy or the precision. In terms of static strain, it's becoming like 10 microstrain. These are the strain that we start to see. It would be good to looking at a pre-warning of how strain is developing. And then the idea is that if you do have that accuracy and precision, you start to see how the pipeline is moving with time. And that's what you see on the Hayward fault case, is that we will monitor, and if Hayward fault moves, maybe the pipeline has not broken, but it has come to certain strain that we can understand. And that makes to David to say, okay, should we replace it or not? Because that gives you the uncertainty to be more certain about what the actual condition of the pipeline is.
Thank you very much. Next question, has East Bay Mud or any other participating agencies implemented any of the center's research and finding in their operations? Part 2 of this question, and what has been the impact?
I mean, the simple answer there is not yet. We've only been at this for a year. We've made some advancements, some early advancements in some modeling, some pipe degradation modeling, some research with some graduate students under Kenichi, and we're also looking at some landslide modeling. So it's given my engineers, my staff, some new information to look at when we're making our decisions, but I don't think we've gotten to the point where we have like final recommendations from findings yet. I think we're still another year or so out on that, but we're on our way. We're on our way. We need to come up with solutions that we can implement at the utility, and so that's really part of what the center is doing. We're taking our challenges. We're going to do research, but we have to come up with solutions, recommendations that we can then act on here at the utility. So we're on our way, and we're seeing some good positive results so far.
Thank you. Our next question, what capital investment would be necessary to implement the fiber optic monitoring discussed during the presentation?
Yes, so the capital investment is like putting the analyzer, that particular box. It's currently expensive, so it's about demand as well. So we want to see people appreciating the value of that kind of data sets, and then engineer will make a better decision. So what we're trying to do is capital investment is actually where probably the most capital investment that you see is people laying the cables in the field, and that particular work and time and the cost is probably the major part, because the fiber is very, very cheap. It's used for telecommunication. And therefore, how can we do a better job in installing these fibers? Then that leads to pipeline companies starting to say, okay, can we put the fiber in their product so that it becomes a market? But then in order for them to do that, David, for example, or infrastructure owners start to see the value of it. And that's what we're trying to do in this particular initiative right now.
Next question, what does monitoring and data collection for the fiber optic equipment pipes look like? So how many data hubs would be needed? And how can the water agencies pivot to include this in operations and planning? So would the hubs need to be physically monitored, like a reading of a meter?
Yes, thanks a lot. So the fiber can go for tens of miles with the one analyzer, one interrogator. So you can have a 24/7 device that is somewhere attached to the fiber, and the fiber is connected to that. But then that may not give you, that may be too costly at the beginning. So what we're doing with Hayward fault case is that our colleagues will go to the site every week or every month to take a gradual monthly reading or weekly reading to understand how the performance of the pipe is. So it really boils down to what the data do you need to make any decision. So at the moment for Hayward Fault, we are taking weekly, monthly reading because we understand the data need is at that particular rate. But then if you start looking at leak detection, then you want to have this interrogator or analyzer running 24/7, and maybe that's another way of investing, but then still the cost may be too expensive. Now we have a project together with a company like where their fiber optics is already installed near the pipeline, where it for the telecommunication. And then what we call them is a dark fiber, where we can attach our analyzer to that already installed fiber nearby the pipeline, and then use that fiber as a leak detection, sort of a monitoring sensor. So that is a project that we're starting together with our colleagues here.
Thank you. So are you aware of any grants available to assist with implementing this technology?
So most of the project we have been working was funded by the National Science Foundation. Grants means funding, is that right, Melissa? I'm trying to, yeah. So obviously National Science Foundation supports us, and then we've been working together with like Caltrans and the oil industry, as well as the PG&E to test these monitoring sensor systems. So they've been providing funding to support. And again, we're working with the East Bay Mud to support this, to see the value for water industry. And then the next step is really working together like Water Research Foundation and the others. But ultimately is really creating a market. So we really want to start implement these technology into your infrastructure, so you start to see the value.
Thank you. I have one more question. Is there a way to update recently installed pipes, let's say within the last 5 years, with this technology without digging up the pipe to apply it?
That's a difficult one. And I think we also want to do some sensing for old pipes. So not only 5 years one, but then older pipes that you may be worried about. But that really boils down to what's the value of sensing of that particular pipe that is under in a difficult position. So like with the East Bay Mud, we've been talking one particular pipe that's being there, but it's a main trunk mains that is crossing a fault. We're thinking excavating and then attaching the fiber and refilling to monitor this pipe. And so unfortunately, we have to excavate and attach it. Obviously, if there's a way to attach it inside the pipe using robotic technology is another one, but then that's a difficult another one. The other thing that we've been talking with some other, like when you do your refit of the pipe, so you put a liner inside. During that process, maybe we can put the fiber between the liner and the old pipe with a grout inside, and then trying to use that as a way to install the fiber optic sensing. But David, do you have some other thoughts?
No, I mean, unfortunately, I think you do have to dig it up right there to put the fiber optics on the pipe that you want to, 40 or 50-year-old pipe that you still want to monitor. I guess the pilot project that we're going to do, Kenichi, with what you call dark fiber, I don't know if that's going to give us any results on the pipe itself, but when we do a test, we're going to do a large-scale fault rupture test in about 3 months, where we simulate an earthquake on a pipe, and then a few feet away we're going to have some fiber optics, and we're going to see what kind of data that provides to us in terms of how the pipe is forming, and maybe that will provide us some information where we then can take advantage of the fiber that's already in the ground right now to monitor our pipelines. But that's a question that we have.
Well, thank you, David and Kenichi, and thank you everyone for your participation. That's going to wrap up our Q&A for today. If you have any additional questions that you think of after this webinar has concluded, feel free to email us and we'll send these over to get them answered for you. Vlad, could you provide some closing remarks?
Sure. Yeah, thank you very much for those very insightful questions. And David, Kenichi, thank you for taking the questions. To me, it's very clear that CSI's mission and research very strongly resonates with the risk professionals and water and wastewater industries. I think it's something that's very near and dear to all of us because of types of issues that we're dealing with emerging risks and claims and lawsuits. And I really think it's a very important subject for us to pay attention to. And when I first got introduced to the center about a year ago, I honestly became one of your biggest fans. And I really appreciate all the hard work that you put into it and all of the research that you do. I would like to ask Paul Fuller from Allied Public Risk to share his thoughts on how the water sector and insurance industry can further advance this discussion. Paul, if you don't mind, could you please share your thoughts?
Yeah, sure, Vlad, and hello, everyone. So from my narrow lens of insurance, I'm seeing two actionable takeaways that impact risk management for the collective water sector. The first is just listening to David and Kenichi. The center's developing practical solutions to mitigate damage to critical infrastructure. It's a big deal. But the bigger deal from my perch is it appears these solutions can present effective litigation defenses for wrongful allegations of third-party property damage arising from or attributed to critical infrastructure. And if we can defend successfully a subsidence claim based on a leaky pipe that wasn't leaking or did not create the landslide or the property damage, that alone is a big win, not just to the water sector, but to the insurance sector, and it provides for a more sustainable and stable cost of insurance. So from my side, I would encourage a call to action with the risk managers that participate in this group to support the center. And it can be through a variety of sources. It doesn't have to translate solely to financial support. The takeaway that I have, my ownership, is to present this to insurers and reinsurers that support the water and wastewater sector throughout the country, but particularly in the Western United States, as well as other viable insurance JPIAs, and to see if we can collaborate and financially support the endeavors of the center. To me, it helps the members. It certainly helps the stability of insurance premium, and ultimately it's advancing a very positive initiative just for the communities that we live in. Vlad?
That's very insightful and I think very valuable thoughts. I really appreciate it, and I definitely can relate to it as a risk manager who has to defend multiple landslide claims, some of them, with demands in excess of millions of dollars. So very, very good thoughts. Thank you so much, Paul. Thank you very much, everybody, for participating in our discussion today and in our presentation. Again, I think we've got some parting thoughts from some of the participants. Thanking David and Kenichi for your wonderful presentation. Our next meeting is going to be held in May, and it's going to be an open forum to discuss ongoing issues that all of us are dealing with in our daily jobs as risk managers. So please try to participate. We will send out invitations. And once again, thank you everyone for your time and participating in our discussion today. Thank you. Bye-bye.
Thank you all.
Thank you.
Thank you.
Bye.